Hi guys, welcome back to my channel. In the last video, I've gone ahead and I've done some long division of polynomial functions and I've found the remainders. Now, the reason that we would want to find the remainder of a function is because specifically we are looking for factors, and we can do that using the factor remainder theorem. So I'm going to use the exact same questions as I did in the last video to show you that these values do actually give you the remainders. All right, so let's go ahead and let's define the following terms. So factor remainder theorem, what is the factor remainder theorem? Well, let's say I have a polynomial and I'm going to call this p of x for the polynomial with respect to x. And I divide this by some linear factor, x take away a. Then the remainder of this particular division is going to be equal to the polynomial when we substitute in the positive value of a. Okay, so what does that mean? All right, so let's think of it this way. We'll start off with a really simple number. So if I have a really simple number like 12, and I divide that by something that I think is a factor, then that is going to have a remainder that's equal to 0. Who cares? Why do we care if it's a factor? Well, because when we have something crazy, so let's just do like a random example. So if we had some like cubic function and we wanted to work out what the factors of this particular function were going to be, because we wanted to put it in some sort of factorized form so that we could graph it, right? It's going to be a lot easier to do that from the factorized form rather than from the original function. So this is just an alternative to something like completing the square or using the quadratic formula, because those tools are really only useful for quadratic functions. They're not useful for cubics. They're not useful for anything for orders of polynomials greater than 2. All right, so let's go ahead and let's jump into those same two questions that we had a look at in the last video. Okay, so x cubed plus 2x squared plus 3x plus 4 divided by this linear factor x take away 3. Now, when we did this using long division, we had a remainder that was equal to 58. So my goal is to show you that if I take my function and I divide it by a linear factor, then when I substitute in the positive value into that function, then I should get the exact same solution. So that's what the factor remainder theorem states. So let's see if this is actually the case. So what's our actual function? Well, our actual function here, p of x, is equal to x cubed plus 2x squared plus 3x plus 4. Our divisor, or our linear factor, is going to be equal to x take away 3. So what I want to do in this case, remember we want to substitute in the positive value or the opposite value to whatever is stated here. We want to substitute that into our function. So effectively, I'm going to substitute in p of positive 3. So that's really important to remember. We're swapping in for the opposite value, the positive version or the negative version if it was originally positive. So let's see if we do actually get a solution of 58 or a remainder of 58 like we predicted we would by doing the long division. So we're going to have 3 cubed plus 3 squared plus 3 lots of 3 plus 4. So simplifying this now, we're going to get 27 plus 3 squared is 9, 2 lots of 9 makes 18, plus 9 plus 4. All right, so these are all multiples of 9, so that makes that nice and easy. So 27 plus 9 is going to be 36, plus another 9 is going to make 45, plus another 9 is going to make 54. 54 plus 4 is going to make 58. And so we kind of already knew this because we've done the long division, but we do in fact have a remainder of 58 when we divide this function through by x take away 3. Let's do another example now. All right, so now we have the second example that we did run through with the long division of polynomials, and from the last video, excuse me, we saw that there was a remainder of -8. So using the factor remainder theorem, I should be able to get this same answer. Okay, so going back, remembering our factor remainder theorem, if I have some polynomial divided by a linear factor x take away a, then when I substitute in the positive value of a, I will get the remainder of that function. Okay, so what that means is we've got our polynomial up the top here, so x cubed take 4x squared plus 2x take 1, and we're dividing this by x minus a. So in this case, because this is x plus 1, we're going to substitute -1 into our function, so swapping in the opposite. So we should have -1 cubed minus 4 lots of negative 1 squared plus 2 lots of negative 1 minus 1. Negative 1 cubed is negative 1. Negative 1 squared is positive 1 times negative 4 is just going to make negative 4 minus 2 minus 1. So that becomes negative 5, negative 7, negative 8. And that's exactly what we saw from the last problem. Okay, so now that we sort of see how this works, where do we apply it? Where do we actually use this? All right, I've got an example here where we're actually going to use the factor remainder theorem to help us decide if x plus 5 is a factor of x cubed minus 19x plus 30. And remember, the reason that we do this, the reason that we want to get functions into factorized form is because it's going to be a lot easier to graph. Okay, so let's go ahead. So our polynomial in this case is going to be equal to x cubed, take 19x plus 30. So we're going to divide by x plus 5. Now, remember the factor remainder theorem, if I have my polynomial and I divide it through by a linear factor, then the remainder will be equal to the value of the polynomial when we substitute in positive a. So in this case, we're going to have a is equal to negative 5. Now, if x plus 5 is a factor of x cubed, take 19x plus 30, it's going to have a remainder equal to 0. So if this remainder does not equal 0, x plus 5 will not be a factor. If this is a factor, then we can go ahead and we can use long division or algebraic methods to find the other factors for this particular function. So let's go ahead and do that. So first we'll test whether or not it is a factor. So we're going to substitute in negative 5, and that's going to be equal to negative 5 cubed minus 19 lots of negative 5 plus 30. Okay, so negative 5 cubed is negative 125. 19 times 5 is 95, and that's a negative and a negative, so that's going to make positive 95 plus 30. So negative 125 plus 95 is going to make negative 30. Negative 30 and positive 30 is going to make 0. So yes, x plus 5 is going to be a factor of this particular function. So what I'm going to go ahead and do off screen is I'm going to go ahead and do the long division, and I will write the fully factorized form for you. So I've gone ahead and done the long division. If you need to refresh this, please do go back to that other video because this video is really just focusing on that factor remainder theorem. Okay, so now what I've got, if I was to factorize this, I have my polynomial is equal to x plus 5, and we knew it had a remainder of 0. So when I divide through my polynomial by x plus 5, I get x squared minus 5x plus 6. Okay, so now because I've got a quadratic, we can solve the roots of this using any method. I think for this one, it's pretty simple to see that this one can be factorized because the factors of positive 6 that add to make negative 5 are going to be negative 2, negative 3. Okay, so now that we've got that in factorized form, it's going to be a lot easier for us to go ahead and sketch this because using our null factor law, we can see that we're going to have the roots at x is equal to negative 5. Oh, that was a bit messy. Let me try that again. Negative 5, positive 2, and positive 3. So there you go. So that's how we use our factor remainder theorem to find remainders when we divide through by a linear factor, but also how we can use the factor remainder theorem to help us to factorize polynomials without having to necessarily use long division to find that first factor. Alrighty guys, I will see you in the next one. Have a good day.